Hi, let's take a look at some trigonometric identities and work out some proofs or show a little bit of the reasoning behind the identities. And so we're working with right triangles. Right, on the unit circle, our right triangle is a radius for the hypotenuse, which is 1 unit. And then we're looking at the ratios of x, y, and the hypotenuse, or the opposite, adjacent, and hypotenuse. We know that a squared plus b squared equals c squared from geometry. And when it comes to figuring out angles, we've got sine, cosine, and tangent as our three main identities. The sine is the opposite, or the y value, over the x value when we make our right triangle. As the angle increases around the unit circle from 0 radians all the way to 2 pi radians, or 0 to 360 degrees. Opposite over hypotenuse is sine, and then cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then we've got secant, cosecant, and cotangent, which are our reciprocal identities. Secant, you can remember maybe the s and the cosine. S and c go together. Secant is 1 over cosine. Cosecant, again, remember the c and the s go together. Cosecant is 1 over sine, and then cotangent is 1 over tangent. So those are our basic identities, and then we can do some algebra, and we have some relationships between the identities. So say we had sine over cosine. Sine over cosine is, again, opposite over adjacent divided by adjacent over hypotenuse. Excuse me, opposite over hypotenuse divided by adjacent over hypotenuse. And then so we're going to multiply the reciprocals here, and we end up getting O over H times H over A. We can cancel out the h's on the top and bottom, and we get over a, which is equal to tangent theta. And so this relates back over to cotangent. If cotangent is 1 over theta, 1 over tangent theta, that means it's also equal to 1 over sine theta divided by cosine theta, or cosine theta divided by sine theta. So reciprocal identities. And then we've got our even odd identities. And so if we look at sine of the negative angle, here's a positive angle starting into the first quadrant, moving counterclockwise around the unit circle. If we take a negative angle, then we're moving clockwise around the unit circle. And so here's negative theta. We can see that if sine theta is y over h, or opposite over hypotenuse, then sine of negative theta is negative y over h, or negative y over 1, because again, the hypotenuse is always the radius, which is 1 on the unit circle. And so then this is equal to negative sine theta, negative y over h. If sine theta is y over h, or y over 1, then sine of negative theta is negative sine theta. Cosine of negative theta is still that x. X doesn't turn negative, and so we've still got x over 8, or x over 1, or x over h, which then is equal to cosine theta. Tangent negative theta, again, we're switching the sign of the y here, and so we're going to get negative tangent theta. Secant, remember this is 1 over cosine here. If 1 over cosine, or 1 over cosine of negative theta is equal to 1 over cosine of theta, that's equal to secant theta. 1 over cosecant negative theta is the same as 1 over, cosecant negative theta is equal to 1 over negative sine theta, or negative cosecant theta. And then cotangent negative theta is 1 over tangent negative theta, or 1 over negative tangent theta, or negative cotangent theta. And then moving along, we can look at our Pythagorean identities. Again, if you imagine a right triangle, which is what we have here on the unit circle, we've got opposite, adjacent, and hypotenuse for the theta angle. And so you know sine squared theta is O squared over H squared. And then we can add to that cosine theta, cosine squared, which is A squared over H squared. And so what do we do here? So this is going to equal, we've got a common denominator. So we've got 1 squared plus A squared at the top. And then, well, let's look at, on our Pythagorean theorem here, we've got a squared plus b squared equals c squared, or a squared plus o squared equals h squared. And so then we've got just that exact same thing here. We've got o squared plus a squared over h squared here. So if a squared plus o squared equals h squared, then we have h squared over h squared, which equals 1. And so then this is our Pythagorean identity there, sine squared plus cosine squared theta is equal to 1. 1 plus tangent theta, or tangent squared theta, well, we know this is 1 plus sine squared theta over cosine squared theta. And then we can do some substitution here. We've got cosine squared in the denominator, so if we want to make 1 into something that we can add to the rest of that fraction there, we can say cosine squared theta over cosine squared theta is equal to 1. Anything divided by itself is just equal to 1. And so now we've got a numerator, cosine squared theta plus sine squared theta in the numerator. And so then what we have here is this is equal to 1 over cosine squared theta or secant squared theta. Because remember here, that's our Pythagorean identity from up here, right? Sine squared theta plus cosine squared theta is equal to 1. And so we've got 1 in the numerator, cosine squared in the denominator. Remember from our reciprocal identities over here, 1 over cosine is secant, and the same is true for 1 over cosine squared. We just have secant squared theta. And then I think you can see where this one's going. If you've got 1 plus tangent squared theta is secant squared theta, then I think it's fairly intuitive that this is going to be cosecant squared theta. But let's go through the math for a moment. Again, we've got 1 plus cotangent is cosine squared theta over sine squared theta. Remember from our reciprocal identities over here, cotangent is 1 over tangent. If tangent theta is equal to over a or sine over cosine, then 1 over sine over cosine is the reciprocal of that, which equals cosine over sine. And so 1 plus cotangent theta then is equal to 1 plus cosine squared theta over sine squared theta. And so then we want to get this 1 to have the same denominator as sine squared theta, so we can work with one single fraction. So we're going to have sine squared theta over sine squared theta is equal to 1. We're going to add to that on the top. Cosine squared theta, we get sine squared theta on the bottom. This again reverts to 1. We can simplify that as equal to 1. So we get 1 over sine squared theta, which is equal to cosecant squared theta. Okay, so those were our main identities, reciprocal identities, even and odd identities, and Pythagorean identities. Let's take a look at sum and difference and double and half angles. In order to find our sum and difference identities, we need to look at a geometric proof, and that's going to lead to our double and half angle identities. Starting with our basic trigonometric ratios of functions, sine and cosine, we're working with opposites over hypotenuse and adjacents over hypotenuse. We've got this angle here, beta and alpha, at DAE or DAB, right? And so alpha can be defined as CAB and beta as DAC. And then we've got a right angle here, so we've got a right triangle at AED. And we're going to work with some of these other triangles here. We've got another right triangle at DF at this point here. We've got another one at DFH. And so those are going to be used for our geometric proof here. We know that these two vertical angles are equal because we've got parallel lines here. We've got a right angle and a right angle, and that's bisected or intersected by AC there. And so if alpha and that vertical angle are complementary, which we know because of this right angle here, that means that this is also alpha, and then that this is also alpha because we've got another right angle here and a right angle here. And so we can start working with DE, so sine alpha plus beta, working with DEA is opposite DE over hypotenuse DA. And that can be split up into GF. GF is part of our height, and then DH or HG is another part of our height there. And so we could have chosen HE, but we needed to use GF because we've got a right triangle here that we can work out. Sine alpha cosine beta. Sine alpha cosine beta is going to be equal to GF over AF. Sine alpha, GF over AF. Here's our hypotenuse, here's our opposite. And then cosine beta. Cosine beta, we want to get AF on the top here because we want to still have GF up here. So we want to cancel out the AFs. How can we make cosine beta with AF? Well, here's cosine, here's beta. AF is the adjacent over the hypotenuse, which is going to be AD again. And so that relates to our denominator up here. These two cancel out, we get GF over DA. And so now we're looking for HG or DH there. Cosine alpha is going to be DH over DF. DH over DF, working with this alpha up here. So we need to construct this model, and we're going to have various alphas and only one beta still. So we need to get rid of the DF. Looking for sine beta now. DF, well, that's our opposite for this right triangle, DAF now, over hypotenuse DA. Rid of those, and we get DH over DA. And so that checks out there. Sine alpha, cosine beta, plus cosine alpha, sine beta. Working down now with cosine alpha plus beta. We're going to have cosine alpha, cosine beta minus sine alpha, sine beta. And so cosine alpha plus beta for this main angle here is AE over hypotenuse, which is still GA. And so we can say that AE is equal to AG, this whole length here, minus EG, or minus GE, or minus FH, because that's the same length there. Let's go with FH, so we can use this right triangle. And that's going to be divided by our hypotenuse DA. And so let's look at cosine alpha, cosine beta. Cosine alpha, cosine beta is equal to AG over AF, AG. Here's our cosine, which is our adjacent side, over our hypotenuse, which is going to be AF. And we want to get rid of, we want to keep this on the bottom here. Right, we want to keep AG on the top, so we're going to get rid of our AF. Looking for AF to be the adjacent side of beta. AF here is the adjacent side of the right triangle TFA. And so if that's our adjacent, our hypotenuse is still DA, which is convenient because we are looking for AG over DA. AG over DA, that's the first part of our fraction here. And so we're going to subtract from that sine alpha, sine beta. And so sine alpha, we're going to start out with FH. FH is our opposite for sine alpha. Looks like we're working with triangle DHF. Our opposite in DHF is HF, and then our hypotenuse is DF. Okay, so we've got HF here on the top, HF, and then we want to get rid of our DF. And we need to have DA on the bottom. Let's just double check if that's sine beta. So we've got DF, correct, over DA. That looks correct. And so these will cancel out. We get FH over DA. And so AG minus FH over DA equals cosine alpha plus beta. All right. Moving along, we've got sine 2 alpha. Well, this is just sine alpha plus sine alpha. And so we can plug that back into our equation here, our identity here. Sine alpha plus sine alpha is going to be sine alpha cosine alpha plus cosine alpha sine alpha or 2 sine alpha cosine alpha. That was easy enough. Moving along, cosine 2 alpha. Well, again, you can plug that back into this identity here. And so we're going to have cosine alpha minus sine alpha, or cosine squared alpha minus sine squared alpha. And so that's just one of our identities, one of the values that we can use for cosine 2 alpha, and the other two are derived using the Pythagorean identity. Remember the Pythagorean identity 1 is equal to sine squared theta plus cosine squared theta. Right, so there's our Pythagorean identity. In this case, alpha is theta. And so we can do a little bit of arithmetic, and we get 1 minus sine squared theta is equal to cosine squared theta, and 1 minus cosine squared theta is equal to sine squared theta. And so maybe you can see where this is going, right? If cosine 2 alpha is equal to this value here, then we can substitute and we get cosine 2 alpha is also equal to, let's substitute cosine squared alpha or cosine squared theta for this value here. We get 1 minus sine squared theta minus sine squared theta, or 1 minus 2 sine squared alpha for our value there. And then we can use this and substitute our value for this here, and we get cosine 2 alpha is equal to 2 cosine squared alpha minus 1. And so, working along with that in mind, so we're using the Pythagorean identity here. Let's just say that we're going to say if alpha is equal to theta over 2, then cosine theta, remember alpha is theta over 2, cosine theta is equal to 2 cosine squared theta over 2 minus 1. Right, because we've got 2 theta, or 2 alpha here is equal to 1 theta. If alpha is theta over 2, then 2 alpha is 1 theta. And so that means that using this here, cosine 2 alpha or cosine theta is equal to, using this one right here, cosine 2 cosine squared, and then remember alpha is theta over 2 minus 1. And so we can just use some simple algebra and solve. We get cosine theta over 2 is equal to plus or minus the square root of cosine, plus or minus the square root of cosine theta plus 1 over 2. So we just move the 1 over the other side, divided by 2, and then took the square root. And finally, bearing in mind again that theta over 2 is equal to alpha, we've got sine theta over 2 is equal to, well, it's going to work out to be plus or minus the square root using this one here, right? 1 minus cosine theta over 2. Right, and then if we wanted to find out the difference values, then we can just substitute in negative alpha or negative beta, and we can come up with those and prove that sine alpha minus beta and cosine alpha minus beta. Alright, look at the values that you can look up in your tables. Alright, so again, starting with this geometric proof, then we can work through these different proofs, and for all intents and purposes, these are best to be memorized, but there's also a lot of handwork and proving that can be done with all of these as well. Okay, thank you.